Welcome all to a new lecture in control system. In this lecture, we will emphasize on steady state error for unity feedback systems. So definitely in the next lecture, we will discuss a much more complex case, that is steady state error for non-unity feedback systems. Myself, Dr. Lalu Seban, Faculty of Department of Electronics and Instrumentation Engineering, National Institute of Technology, Silchar. First of all, we'll see the objectives of today's lecture. We will review closed loop control system. We'll try to understand the difference between transient and steady state error. We'll see how to calculate steady state error, define type number of a system, and we'll also define static error constants. And we will understand how the type number of a system affects steady state error for different kinds of typical inputs. Here inputs means the reference signal. So coming to the introduction, closed loop control system. So this is a very well known block diagram for any student in control system. This is single loop or single input single output feedback control system. Closed loop control systems are designed to automatically achieve and maintain the measured process variable equal to the reference in spite of disturbances and timely changes in reference value. The major components of a single input single output closed loop control system include a controller, final control element which is also known as actuator, sensor, in addition to the main process. Controller, actuator, sensor are individually unique systems with their own inputs and outputs. These systems are connected in a certain pattern to get a closed loop system. So now let us see the various signals that are present in this system. First of all, as I have mentioned, the reference signal. This is also known as set point. The reference signal and set point here represented by using the notation R. Then the actual process output, I am emphasizing on actual for a particular reason. This is also known as process variable. This is represented by the notation Y. Then the feedback or the measured value of the process output. Okay, so there is a difference between the actual process output and the measured process output. The measured process output is represented by Y subscript M. Ideally, the measured value should be very close to the process output. For reducing the complexity in many cases, we assume that the dynamics of the feedback component as unity. The sensor plus the signal conditioning setup, whatever it is, we will ideally assume it as unity. Such systems we will call as unity feedback systems. So the dynamics of this feedback part will be unity. Then in that particular case, when the dynamics of the feedback part is unity, then the measured output by M will be equal to the process output. Now another important signal is the error signal. It is represented by the notation E. That is the difference between the reference signal and the measured output. So the error is equal to reference minus measured output. Control output is represented by a notation CO. Actuator output is the input to the process, and the actuator output is also known as manipulator variable and represented by using the notation M. So here the output response depends on the process dynamics and the dynamics of all the components and the reference signal. One of the main objective of any closed loop control system is to get the output, the process variable, to as close as to the reference signal. So the reference signal will say what should be the process variable. So in other words, when y of t will be very close to r of t, error will tends to 0. Errors in a control system can be attributed to many factors. First one, imperfections in system components. There are many possibilities of imperfections such as static friction, backlash, amplifier drift, as well as aging of components. Then inadequate signal conditioning or noise in the feedback loop. Another main reason is the process disturbances. Here our emphasis is on error due to changes in the reference input. Whenever there is a change in the reference input or set point, definitely output will also change to track the set point, but it will not track the set point instantaneously. There will be a time gap. So during the time gap, there is possibility of two errors. Not possibility, there's definitely there will be two sets of error will happen. First one is the transient error. So this is due to the short-lived burst in the response of a system caused by the change in reference. The second one is a steady state error. It is due to the long-lasting effect in response of a system caused by a change in reference. So definitely any change in reference input will cause unavoidable error during transient periods and may also result in long-lasting error. The steady state error, it is a trickier part. It depends on many things. It depends also on the stability of the system that we will see some other lectures. So the steady state error, which is represented by this notation, is a difference between the reference and the process output as time tends to infinity. In this lecture, we shall not discuss errors due to the imperfections in system components. We have seen different cases. Rather, we investigate a type of steady state error that is caused by the incapability of a system to follow particular types of inputs. Here in this slide, if we just look into this particular slide, it is very familiar to you people. It gives a trend of output Y error for a unit step change in reference for a second order underdamped system. This is a second order underdamped system. So this indicates the process output. Second order underdamped system. So there are oscillations, overshoot, and all. And here the delay time, rise time, peak time, settling time, all are indicated. It is getting settled around some 100 units of time. So the input, the reference signal, as I have mentioned, is a unit step. At the end, it is settling at around 0.9. So after a long period of time, it is settling to a value of 0.9, which is not equal to the reference. So the difference between the reference and the process output, that is 1 minus 0.9, which is equal to 0.1, is a steady state error. It's a steady state error. So this dynamics, the process output dynamics, is very familiar for us. Let us see the error dynamics. So error, as we have discussed, which is the difference between the set point or the reference and the process output. So the reference is the unity signal, is a unit step basically. Till time t is equal to 0, it will be 0. At time t is equal to 0, it will jump to 1. It will remain at 1. Now this is the process output dynamics. So the reference signal r of t minus y of t, this will give the error dynamics. Okay, we can clearly see the error dynamics in this red plot. Okay, initially there is a transient state. Transient stage will be, say, somewhere near to 100 units of time. Later it is settling to a value of around 0.1. Yeah, because 1 minus 0.9, it is settling to 0.1. So in this figure, we can see the relation between the reference, the output, and the error. Here we can easily differentiate between the transient state and the steady state. Now, as we have discussed, today's class will be on the steady state error. So the previous closed loop system, these are the Laplace representation of the previous closed loop system representation. In the blocks, we are having the transfer function of controller, the final control element, process, and the sensor and the feedback loop. And these are the Laplace transform of the signals. So a reference, error, control output, manipulated variable, output variable, and the measured output. So what is our main focus? Our main focus is on the error, in particular steady state error. Two different kinds of references. How the error dynamics, how the error or how the steady state error depends on different kinds of references for different kinds of system dynamics, definitely. So let us try to understand the relation between the error and the reference signal. So applying the block diagram reduction, the three blocks in the forward path, that is the controller, transfer function C of S, the file control element or actuator transfer function GV of S, the process transfer function GP of S, all three are cascade. So it is cascaded together, and this is the net transfer function G of S. H of S, as represented earlier, it is the feedback path transfer function. So from here it is very clear that the error E of S it is equal to the reference minus the measured process output, that is reference R of s minus Ym of s. Now Ym of s, it is equal to h of s into y of s, because these are in Laplace domain, and output of any system is the product of the system transfer function and the input. So the output of h of s, which is Ym of s, is a system transfer function h of s multiplied by the input signal in Laplace domain, that is y of s. Then again the same principle we can apply here. Here y of s is the output signal, which is nothing other than the product of the transfer function g of s and the input e of s. So replacing y of s as g of s into e of s, we will be having this representation. Now taking all the error components, that is e of s, to the left hand side and rearranging the equation, taking common things and rearranging the equation, we will be getting e of s to r of s is equal to 1 by 1 plus g of s into h of s. This is a very general case, and this transfer function, this relation e of s to r of s gives for non-unity feedback system. Okay, h of s is not unity. So as I have mentioned in the objective, today's discussion is emphasizing on unity feedback system, because in many cases we can have a very good approximation that our feedback system is having unity dynamics. Whatever is a process output, it is clearly represented by the feedback system, that is Ym of s will be equal to y of s. That is a very good approximation. So for unity feedback system, when h of s is equal to 1, Ym of s will be equal to y of s, and our new relation e of s by r of s can be given by equation number 2. So our emphasis is on the error signal. So e of s will be 1 upon 1 plus g of s into r of s, that is the Laplace transform of the reference signal. Now we are interested in the steady state value of the error. So since this is in the Laplace domain, we can easily apply the final value theorem. So the steady state error, that is error at time t tends to infinity, will be limit s tends to 0 s into e of s. So rewriting e of s, it will become this equation number 4. I just want to recall one thing at this point of time. Final value theorem can only be applied if the subject of the limit, okay, in this case the subject of the limit is s e of s, has poles with only negative real part. Please be careful. Now here onwards we will see the steady state error for different standard inputs: unit step input, unit ramp input, and unit parabolic input. So we will be mainly seeing it for these 3 cases, because many other signals are combination of these 3 signals, can be made as a combination of these 3 signals. So in order to explain how these test signals are used, let us assume a position control system where the output position follows input command position. So it is very easy to assume steps inputs that represent constant position. Step input is a constant position once it change from one position to another position, and thus are useful in determining the ability of the control system to position itself with respect to a stationary target. The Laplace transform of unit step input is 1 by s. Steady state error by applying final value theorem, rewriting R of s is equal to 1 by s. We will be writing it as equation number 5. So g of s, we don't know what is the transfer function. It will vary. So in general, we can write it as 1 by 1 plus limit s tends to 0 g of s. This limit s tends to 0 g of s, we will call it as position error constant, Kp. Okay, position error constant, because as I have mentioned, position. So in order to have a 0 steady state error, what should be the value of Kp? Kp should be infinity, right? If Kp is infinity, this will be 1 by 1 upon infinity, which will be 0, which implies that g of s should have a form. Okay, here g of s is represented as gain 0 pole form. It should have a form in which n should be greater than or equal to 1. If n is equal to 1, substituting here, when s tends to 0, we will be getting g of s is equal to infinity. That is the case for n is equal to 1, 2, 3, whatever it is. So let us conclude here one thing. When we are having step input, if n is greater than 1, the steady state error will become equal to 0. Now, what does it mean? If n is equal to 1, s raised to n, that means there is a pole at origin. S square, that means there are 2 poles at origin. So, the number of poles at origin is having an effect in the steady state error. Now let us go to the next case, that is for a unit ramp input. So before going inside, ramp inputs represent constant velocity inputs to a position control system by linearly increasing amplitude. These waveforms can be used to test a system's ability to follow a linearly increasing input or equivalently to track constant velocity target. For example, a position control system that tracks a satellite that moves across the sky at constant angular velocity. So the Laplace transform of ramp input, unit ramp input, is 1 by s square, replacing R of s in the equation, steady state equation for steady state error. So 1 s into 1 by s square. So s will 1 by s will be there. So it will be 1 by s, that means 1 into s plus s into g of s. Applying the limit, s tends to 0, this part will become equal to 0. Then it will be limit s tends to 0, s into g of s. I hope it is clear. So this time limit s tends to 0, s into g of s is called as velocity error constant. Okay, there is a difference. Previously we have seen position error constant. Here this is the velocity error constant kv. Now let us look at kv. What condition of kv will give us zero steady state error? Very simple. If kv is equal to infinity, we will be having zero steady state error. How it is possible? Say g of s, when it is represented in gain zero pole form, if the number of poles at origin is greater than or equal to 2. So if consider the case when n is equal to 1. If n is equal to 1, what is going to happen? This s and s will get cancelled out. So substituting s is equal to 0, s tends to 0, we will not get infinity in the denominator. That is not going to happen. That is same for n is equal to 0 also. But for n is equal to 2, 3, 4, we are going to get the denominator part as infinity. So concluding this particular slide, for unit ramp input, the steady state error will be 0 if the system g of s is having 2 or more poles at origin. Now let us go to the next case, that is for unit parabolic input. Parabolic inputs are having second derivatives are constant. It represents a constant acceleration. So with respect to position control system, this can be used to represent accelerating targets such as missiles. The Laplace transform of unit parabolic input is 1 by s cube. Substituting r of s in the steady state error equation. So here, so s and s will get cancelled out. It will be 1 by s square. That will become, in the numerator part it will be 1. In the denominator part it will be s square plus s square into g of s. Applying the limit, s square part tends to 0. Then what will remain is limit s tends to 0, s square into g of s. Now again, to have 0 steady state error, this denominator part should be equal to infinity. So before that, this denominator part, that is limit s tends to 0, s square into g of s, that we will call it as acceleration error constant, Ka. So there is a difference between Kp positional error constant, Kv velocity error constant, Ka acceleration error constant. You may go back and see the difference once again. So the acceleration error constant should be equal to infinity to have 0 steady state error. That implies when it will become equal to infinity, if g of s, okay, which is represented in gain pole 0 form, should have more than 3 poles at origin, right? If there is 3 poles, if there is more than 3 poles, s square and s cube, s square will get cancelled out, then remaining 1s will be there. That will make the denominator part to infinity. If there is, say for example, if n is equal to 1, what is going to happen? N is equal to 1, here s is there, s square and s, the denominator part will get cancelled out, then s into g of s, that means limit s tends to 0 into s, that means this part will become equal to 0. So the steady state error will not be 0. So concluding this slide, when you are having unit parabolic or parabolic input, to have a 0 steady state error, the forward path system g of s should have at least 3 poles at origin. So all the 3 cases that we have seen, the steady state error for unit step, unit ramp and unit parabolic inputs are for unity feedback system. Please take care of that. Now I just wish to introduce a new term to you, that is type number of the system. The type number of the system indicates the number of poles at origin for any given transfer function. So this value help us to indicate whether the steady state error of the system will be 0, constant or infinity. So this is a general representation of unity feedback system, definitely. So the forward path gain g of s, the forward path transfer function g of s is represented by gain 0 pole form. Here n indicates the number of poles at origin. Here n again represents the type number and the number of poles at origin, both are same. So it is different from the order of a system, please remember. Now, how the type number of the system and the steady state error are related. First of all, let us see how the type number of the system and static error constants are related. So for type 0 system, for step input, Kp is constant. For type 1 system, for ramp input, Kp is constant. For type 2 system, for parabolic input, Ka is constant. And the infinity case already we have seen. Now for type 0 system, for type 0 system, Kv and Ka value will be also equal to 0. You can go back and just compare. Now for type number and steady state error. Okay, for step input, the steady state error is 1 by 1 plus Kp. Ramp input it is 1 by Kv. Parabolic input it is 1 by Ka. Since you are having the previous table, calculating the steady state error is very easy. Kp is constant here. So 1 by 1 plus Kp will be again constant. So for type 1 system, Kp is infinity. 1 divided by 1 plus infinity. So 0. Type 2 system again 0. For ramp input, we can see that for type 1 system it is constant, the steady state error is constant. Type 0 system steady state error at time t tends to infinity, it will become infinity, very large value. And for type 2 system it is 0. Parabolic input, it is constant. For type 2 we have seen, if we just compare the previous case, for parabolic input for 0 steady state error, the type number or n should be greater than or equal to 3. If it is 2, if n is equal to 2, we can see that we are going to get a constant value. If n is equal to 2, the square and the square will get cancelled out and you are going to get a constant value. If type number is equal to 1, the steady state error will be equal to infinity. Now there are 2 exercise problems for you. Draw a rough plot of output y of t and error e of t for the following forward path transfer function. Again, this is for unity feedback system. The system is excited by unit ramp. Okay, we are having 3 cases. If we just look into this, what's the difference between the 3 cases? The first case, type number is 0, second case type number is 1, third case type number is 2. Just for you, the third case the type number is 2. What is the transfer function? What is the order of the transfer function? Can you just answer that? It will be definitely 2 plus 1 plus 1. It is 4. Okay, the order is 4 here. Type number is 2. Now let us see a more complex problem. A reference signal is represented like this. Okay, so this is a combination of step, ramp and parabolic signal. The reference signal is a combination of all three standard signals. It is given to a unity negative feedback control system with forward path gain. Forward path gain is given like this. So by just looking at the forward path transfer function, you can see the type number is 2. The question is find the values of static error constant, that is what is the values of Kp, Kv and Ka. Also find the steady state error. Fine. Thank you. Wait for the next lecture.